Okay, come on. Let's start for today. Alright, so today, last lesson we concluded Chem bonding, right? Okay, next week, then I will start a new chapter called gaseous state. Okay, but I don't want to go too fast. Okay, so today we're just gonna take a step back, right? Look at whatever we've done in Chem bonding so far. Okay, so on top of the tutorial, right? I feel that the tutorial is not enough. So I'm gonna give you guys more questions here to practice today. Okay, so for today, right, what we're going to discuss first, okay, I will cover whatever we've covered before, and then today we're just going to dive straight into the questions. Okay, so I hope you understand, right? Chem bonding, there are a couple of core ideas. Okay, core ideas meaning, right, what you should be minimally studying when you look back at this chapter. Okay, number one, right, will be structure and bonding. Arguably the easiest idea in this chapter. Okay, I think this one is quite simply covered. It's just a lot of content only. Okay, and then we proceeded over to BSEPR theory. So over the span of the 5 lessons, right, BSEPR theory took about 2 lessons, okay, including drawing dot and cross diagrams. Okay, so this is a rough idea of what we have gone through so far. And then the third one, right, was on intermolecular forces. Okay, so intermolecular forces is probably, I would say, the core of the core ideas. Because in future chapters, right, we are mostly going to be looking at intermolecular forces because it plays a vital role in explaining physical properties. So in a lot of the organic chapters that we will eventually touch on, right, there will be callbacks to physical properties. Like we can even use intermolecular forces, right, to explain physical properties of organic compounds. That's why you start to see this appear a lot in future chapters. Okay, so for today, right, our goal is to iron out all these concepts, okay, so that in future we don't really have to worry about it too much. So we start with something simple first. Okay, I need you guys to look at question 1. Okay, and generally how we do revision lessons is this. I will need to time you guys because time management doesn't start one month before the exam. Okay, it starts right now. Okay, so let me just introduce to you guys, right, how time management works in JC. Okay, in a JC paper, 1 mark is 1.5 minutes. Okay, but I don't expect you guys to be able to hit 1.5 minutes per mark. Okay, because this is a bit challenging for you guys who just started out. Okay, this is what we aim to work towards. Okay, so for now, we can still afford to have like 1 mark for 2 minutes, something like this. Okay, but we won't really go over this as a very strict way of allocating time. Like for example, if you look at question 1, right? Okay, we have a total of 3 marks, right? Okay, but I won't multiply by 1.5 minutes. Okay, we try to aim a bit lower. Okay, that's how I will do things. That's how we train time management. So for question 1, I will give you guys 4 minutes. Okay, you guys see whether they hit this timing. If cannot, I will gladly increase the timing over the course of how long you take to do this question. Okay, so I'll time you guys. Okay, so for 4 minutes, right? Okay, you can start now. Okay, do the first 2 parts. Right? Okay, we need to refer back to the notes. Go ahead now. Okay, again, the content is not what you guys are going to struggle with, it's the application. Okay, so it doesn't matter whether you refer to the notes or not. If you guys move on to part 2, right, there's only one thing I need to tell you guys. Cyclohexane has a molecular formula of C6H12. That's the only thing that I need to tell you guys to do this question. Okay. We have roughly 2 minutes left. 1.5 minutes left. Okay, 1 minute left. Okay, just about 15 seconds left. Okay, then we'll go through. Wait, what's your CC again? Quite correct. I heard there's a lot of people in correct. Like a huge acceptance rate. Yeah. Wait, do you know this girl called? But I think she also said she's incorrect. Don't do a lot of things. You don't even know what you're doing there yet. Oh, you're going to start again. But Isabel looks like she's in all the CCAs, concert, concerts, sponsorship, everything also. Oh. Okay, come. Okay, let's go over the answers. Okay, so that was about 4.5 minutes. Okay, so rather healthy estimate. All right. Okay, the first one I want to go through is IQ minus. Okay, I'm sure you guys are able to spot which kind of concept this all falls under. Okay, solubility falls under intermolecular forces. This is clearly on DSPR, dot and cross. Okay, IQ minus is one of the more tricky structures because I show you guys some common answers first. Okay, you always have to deal with the charge, and you all remember when you have a negative charge, when do you add it? You add an electron to the. Is it the central atom? No, not the side atom. Okay, so remember, you add an electron to the more electronegative atom. As for a plus charge, you remove from a less electronegative atom. Remember the rules are, okay, it's nothing about center or side when it comes to charges. Okay, but in this case, all of them are equally electronegative, right? So the question is, do we add to the center or do we add to the side? Okay, so guys, let's look at it first. Initially, iodine has 7 valence electrons, right? Guys, when you add the 1 electron, who do you guys add it to? Okay, let me hear from you guys. Okay, where do you all add the 1 electron to? To the side iodine or to the center iodine? Which one do you all choose? Okay, use center. Okay, but some of you may use the side. Okay, let me just consider both answers. Okay, so if you add to the center, this guy has 8 valence. Okay, and then the side atoms right can form how many bonds with 7 valence? 1 bond, right? Now 1 bond, I'm just going to draw this instantly. Fill up all the other valence. Okay, 1 bond, fill up all the other valence. Okay, then for iodine in the center, how many more do I need to fill up? Okay, how many more do I need to fill up? Okay. 8 valence. So I draw 2 already. So we left with 6. 6 comes in the form of 3 lone pairs. Now is this acceptable? Okay, iodine in the side has 8. This guy also has 8. This guy has how many? Okay, 10. Is he allowed to have 10? Yes, okay, because he is below period 3, right? Okay, so everything seems fine and dandy. However, this is not the correct answer. Okay, I will explain you guys later. Okay, for now, let's look at the correct answer. Okay, instead of adding to the side, I want you guys to write down the electronic configuration, not the configuration, but the number of valence electrons that each iodine has. What we need to do in this question, right, is to actually add the electrons to the side item. Okay, there's no hard stone cold rule over here, right? That says that you need to add to the side atom. All the negative charge says is you must add it to the more electronegative atom. But the issue is I don't know whether to add it to the center or the side, right? Okay, let's see. Why do you need to add it to the side? Later we will discuss, but now we just do first. When you have 8 valence electrons on the side, right? What kind of bond can you form? 8 valence at the side. So you can only form a dative bond, right? Okay, so a dative bond, I'm just going to give it to the guy in the center, and then basically it has 8 dots looking like this. Make sense? Okay, then how about the iodine at the side? 7 valence is 1 bond, right? So instantly do a 1 bond, so dot cross looks something like this. And then how many electrons do I need to fill up on iodine? 6 more, right? Because 7, I already used 1, so 6 more is in the form of 3 lone pairs. Now, some of you may be asking me, right, what on earth is the difference between this one and the one that we drew just now? The only difference is the dative bond. And some of you may be arguing and saying that, hey, I thought dative bond is meant to be the last resort, like what I taught you guys. Okay, but this is actually the answer, right, for a very separate reason. It's very contextual. Okay, and I don't want to tell you guys the answer straight up. I want to hint the answer towards you guys up. Okay, but this is the correct answer. So maybe I want you guys to draw the structure also. The structure, meaning to say you only draw the lone pairs on the central atom, and then the dative bond is actually looking like this. Now, I used to tell you guys that the dative bond is always the center given to the side, right? But this is a special scenario. You will see why in a short while. All okay first, in regards to the drawing. All okay, now, let's see why it has to be 778, not 787. Okay, you guys look at the question now. The only thing I want to point to you guys is this. I want you guys to take a look at this equation. And can you guys possibly tell me why, right, it has to be this configuration and not this? The clue lies in this equation here. Any idea? Think about it. Okay, so you have the rough idea there already. Okay, so let me translate. Okay, guys, I2 in itself, right, is 7 electrons, right? Then they share a single bond. Agree first? So that's iodine. However, how do you form I3 minus? It's because you're adding I minus to iodine. Make sense? How many electrons does I minus have? I minus has 8 electrons. And because of that, right, we have an I minus sitting over here, okay, looking like that. It has 8 electrons with a negative charge. So that's why, right, how this works is it takes one lone pair and donates it to the central atom like this. Okay, so then the lone pair, let me just put it at the side also. So that's why, right, it should be 778. It doesn't make sense for it to be 787 because we started off as I2. I2 is 77. Does that make sense? There's no possible way, right, for the 8 electrons I minus to sandwich itself between 7 and 7. Can you all see this looks a bit ridiculous? You have 2 iodines, right? And then the I minus comes in the middle. That doesn't make any sense. Okay, it can only attach itself by the side. So that's why this is a very novel question. A lot of people get this question wrong because this looks very logical. And then I told you guys that dative bond should be the last resort. So you'll choose this instead. Okay, but you must look at the formation of this guy. Okay, now in school, right, maybe your teachers have told you guys similar looking ion. You guys can also try N3 minus. This is known as an azide ion. Okay, RJ likes to commonly test this. This came out for a whole paper maybe 1 or 2 years ago. Okay, so once again, I thought I cross in exam, you will test something very easy. Okay, go and try N3 minus yourself. Okay, if you can't draw, then you can come and ask me separately. Okay, but for now, let's look at a simpler question, which is the second part. Guys, solubility question, first thing you need to underline is insoluble. Okay, because again, I told you guys, you need to explain things that are already given to you guys. Okay, whatever that's there, you explain. So I told you guys C6H12. Okay, can you remember a bit of solubility concepts? Look at this diagram here, let's fill it up. Can you tell me C6H12 is a what kind of molecule? Okay, covalent, everything is covalent here. Okay, we are talking about the polarity, right? Is it polar or non-polar? Okay, non-polar. How do we know that? Because carbon and hydrogen are non-polar bonds. Agree? So I only needed to tell you guys it's C and H. I don't have to tell you guys anything else. You can figure it out yourself. Okay, so it's non-polar, whereas water is a what kind of molecule? Polar, right? And I remember telling you guys, if you have a non-polar and polar molecule, are they compatible with each other? No, that's why you can expect an insoluble solution. Make sense? Okay, so let's identify everything first. C6H12, what's the interactions? Ideally, very good. Okay, how about water? Okay, water is just your classic hydrogen bonds. Okay, and guys, can you tell me when they try to form some sort of interactions, is what kind of interactions? They are not compatible with each other. They don't like each other. So the attractions are bound to be weak or strong. Okay, very weak, right? Okay, so what's the weakest form of interaction you guys know? ID-ID. Okay, so you can clarify that this is a weak ID-ID attraction. It is insufficient to compensate for the attractions they are trying to break. Does that make sense? So in this case, what we have is just fill in the blanks. Okay, this format of answering, right? Okay, maybe now you need to copy from your notes. Okay, but I suggest every time you copy, you must tell yourself the next time, right? Try not to copy again. Okay, so you must resist the urge to copy. So every time you copy, you must tell yourself no more next time. Okay, so energy released from the weak ID attractions is insufficient to compensate to overcome the ID in C6H12 and hydrogen bonds in water. Generally, if you can draw out this diagram, you can already ask. So you can first start with the work for this question. Okay, it's good to put the word weak. If you don't put the word weak, it's fine. Okay, but what I like to put the word weak here, right, is to really show that they are not compatible with each other. So the attractions are already bound to be horrible, right? That's why I use the word weak. Because on the other hand, right, if you have two non-polar molecules, okay, guys, you take a look. If you have two non-polar molecules, what kind of interactions can they form with each other? Okay, imagine this scenario. I have a molecule A and molecule B. Both of them are non-polar, right? What kind of interactions will they form with one another? Also ID, right? Guys, because we already mentioned non-polar molecules only have ID attraction. So there's nothing else they can form. But are you trying to tell me that this ID is very weak? Is this a weak ID attraction? No, right? Because we know that they are very compatible with each other. So the word here is favorable. So the strength of the ID depends on the context. If you have a context like this where they don't like each other, ID is weak. But if you have a context where both are non-polar, they are favorable. It's still ID, yes. Objectively, it's weak, yes. But in this case, it's strong enough to overcome its own existing ID attractions. So that's why words like these are very good. If it's soluble, you can use the word favorable if they both share the same interaction. If it's insoluble, you can get across the idea that the attractions are terrible, they're weak. Make sense? Okay, so one little question like this, so many things we can talk about. So far, any questions? Okay, don't have, right? We're going to try the second question, which is honestly still a warm-up question, nothing too difficult here. Okay, I'm going to give you guys a total of 6 minutes, right? Okay, for the whole of question 2. Not much to explain. Okay, in fact, it's an application question. Okay, so let's see how your application is like. Right, question 2, I give you guys 6 minutes. Okay, we start now. we have about 3 minutes left. Okay, try not to be too stuck on the first part of the question, because after all, right, it's only 1 mark. Okay, there might be other 1 marks that are way easier to get in the rest of the question. Okay.
My comments.
Yes.
Your top 10 is without extra audio. I know. Like, I think definitely yes, definitely. Okay, 4, 10, so I said because it's not many, but then everything else good and good. We did what they this you don't but if the one you compare, I don't think to 1 or 15. 对，哎，有三个月了，115 only, right? You haven't set more as 1 hour 15 minutes. They also are a single speed.
I see again. Yeah, I'm doing also. That's why I'm booking the class. Yeah, actually, it's Thursday.
You might ask your. You can ship a. And I think as in not the detail. So try to do yeah.
Let me know when you guys are done. Okay, 30 seconds before we hit the 8-minute mark. Right? Okay, need more time? Okay, so time's up, right? Okay, so let me just talk a bit about time management first, because it's a skill that we need to start early so we are more prepared for the exam. Okay, a lot of people tend to fail the paper, right, because they cannot manage their time. So let me just tell you guys what just happened. Okay, you guys took 4 minutes just for the first part. Yeah, okay, and that, right, is what we like to call the lack of a red flag intuition. Okay, so this sounds like a very cheap, fancy term, right? But what I'm trying to say is this: I'm slowly trying to build this skill. Red flag intuition is if you see that a question, right, isn't worth your time, you should move on. Okay, you shouldn't try to spend too much time writing an answer for just a 1 mark question also. Okay, so you need to gauge your own time. As what I mentioned, right? Ideally, 1 mark is 1.5 minutes. So if you spend more than 1.5 minutes, or you can foresee yourself taking more than 1.5 minutes for this question, right? Try to move on first. Because you never know, some of the 1 marks in the later parts of the question might be easier. Okay, based on your own experience with this question, you might think that this part is actually easier than part 1. Okay, so that's what we need to learn how to do. Know when to give up and know when to move on from questions. Okay, because if you sacrifice too much time on just 1 mark, right? Okay, in the rest of the questions, you might not even be able to have the chance to get the marks. Okay, now ideally, right, because you guys are still a little bit early in the year, right, you can still afford to go a bit ahead of time. So 1 mark, you can give yourself 2 minutes. Okay, so we took 20 minutes for this whole question, which is okay, but not the ideal. Okay, what I usually like to do is to undercut you guys. So I will sometimes give less time for each question. Okay, the reason behind that, right, is because we need to train it from the back, train a little bit harder, right, so that we can hit this target eventually. Okay, so time management, very important. Okay, so for this one question, right, you can already see part D is not very worth 1 mark. For 2 marks, okay, maybe it's worth it. Okay, for 1 mark, definitely not. Because why? Number one, you guys need to draw out the structures of carbon dioxide, and you need to recognize the shape immediately. Guys, take note, carbon dioxide is a common structure. Okay, you shouldn't need to draw out the dot and cross and convert. That takes too much time. So let me give you guys a list of common structures where you need to know the shapes for. Number one, carbon dioxide. You definitely need to know the shape. Next, water. Water is a bend shape. You need to recognize the bond angle, the shape, and all that. Okay, next, ammonia. Ammonia has a trigonal pyramidal shape, very, very commonly used. Finally, CH4. CH4 has a tetrahedral shape. Okay, why these are common compounds? Because they have some of the most basic looking shapes and bond angles. So you must be able to recognize these structures and their shapes immediately. You cannot spend time in exam thinking of their shapes. So I tell you all in advance first. Okay, so carbon dioxide is one of them. You know it's 180 degrees. SO2, on the other hand, isn't a common compound, but you still, okay, that's where you spend your time drawing the structure. Okay, you draw already, you recognize the shape. It should be 180 degrees from our syllabus, but it says approximately 120 degrees. Now, guys, the only thing to explain these, right, is what? Why are their bond angles so much bigger? Okay, it's because if you all look back at BS-EPR theory, we are meant to look at the repulsions, right? Okay, can you all tell me what's the repulsions in carbon dioxide? You only have a bond pair repelling with a bond pair, yes. The bottom side is also bond pair repelling with bond pair. So that's why both top and bottom are equally repelled. Whereas this is not equally repelled because the bottom side is bond pair, right? Whereas the top side is lone pair, bond pair. And as we know, our lone pair, bond pair is much stronger. That's why it squeezes the bottom a bit smaller. So that's how you explain this question. All you need to tell me, guys, the reason why it's 1 mark is because all you need to tell me is this. Lone pair, bond pair repulsion in SO2 is stronger than the bond pair repulsions in carbon dioxide. Finish. Then if you really want to end off your answer, you can tell me that's why SO2 has a smaller bond angle than carbon dioxide. Or you don't even need to write than carbon dioxide because you don't have time. Okay? This part here doesn't get you the marks. The marks, right, is to specify the repulsion types and to compare the strength. That's all for 1 mark. So they don't give 1 mark because of how long you take to do the question. It's how much you are required to write for the question. That's it. Okay? And Okay, then we just quickly move on to this Van Alkel triangle because I want to move on to more challenging questions really. Okay, now you take a look at this triangle, right? Okay, I'm pretty sure you guys can figure out what it all means. You have never seen a Van Alkel triangle before. That's why you need to learn on the spot. How do you learn on the spot? We facilitate that by giving you guys an example, right? So can you tell me what 2.75 represents? Okay, average electronegativity. Even I also don't know, I must figure out on the spot. Okay, because we don't know what Van Alkel is. Okay, and 1.7 represents the difference in electronegativity. Read the question carefully, right? They confirm will tell you enough information. If they never tell you enough information, that means the question got problem. Okay, but that will not be the case, huh? Okay, things like this when you never see before, everything in the question is necessary, is enough, is sufficient for you to do the question. So the answer for carbon dioxide is very simple, right? 3.05 and 1.1. Then you go plot on the graph. Okay, on the graph, right, it should be somewhere here if I'm not wrong, and then you're going to label it carbon dioxide as well. Okay, so you see, guys, is the 1 mark here easier to get or the 1 mark here easier to get? Definitely here, right? Okay, that's why you need to know when to move on because you never know what lies ahead of you. It might be easier. Okay, guys, let's look at part 2. Can someone tell me what's the type of bonding in part A, in point A? What's the type of bonding? Answer for A is metallic bonding. Oops, I spelled metallic wrongly. Okay. B should be covalent bonding. Can you all justify why? I know they never ask for justification, but can you all perhaps try to verbally explain and see whether you all got the correct idea? Because you never know, it could be a fluke. And then when you all really are required to explain, right, later come out the answer wrong also. Okay, guys, what is A metallic bonding and B covalent bonding? Okay, when you all first look at A and B, what similarities do these 2 points have? A and B both have no electronegativity difference, right? Which implies both atoms are probably the same. You might instantly think of covalent bonds where the 2 atoms are the same, right? But what's the next thing? What's the difference between A and B? Clearly, B has a higher electronegativity than A, right? So how do you determine that? How do you know A is on metals? Okay, good. Metals are on the left side of the periodic table. You should know, left side of the periodic table is low electronegativity. Right side, covalent bonding is made out of what usually? Non-metals, right? And non-metals are on the right-hand side, so they should have a higher electronegativity. That's it. You don't need to explain in this case. You get how many marks here? I think 1 or 2 marks, right? Okay, you can already see for 1 mark only. Okay, but it's more worth it than whatever we did just now. Last but not least, guys, what's the answer here? For the last part. Okay, answer here should be more ionic. Okay, so a common answer is that some of you guys will put less ionic, right? I'm going to offer you guys 2 explanations. The first explanation utilizes the Van Alkel triangle. This guy Van Alkel, right, didn't create this, right, and for no reason. Okay, this guy spent like half his life studying this shit. Okay, next, I'm going to show you guys the reason that we learned it on syllabus. Okay, so we use the exam question first because they gave it to us. Okay, let's not put this guy's efforts to waste. Okay, so Al2O3, Al2H3, right? The only difference is oxygen, right? Oxygen, you see our Van Alkel triangle uses electronegativity, right? So we discussed. Oxygen is more or less electronegative. More, right? Yes. Okay, guys. If you're more electronegative, that means the electronegativity difference in Al2O3 has to be larger or smaller? Larger. So you can use the triangle to your advantage, right? Since you already figure out all these 3 points, you can see the higher the electronegativity you are leaning towards ionic. So more ionic. That's it. That's an easy way to do this question. I'm going to recap to you guys the way that we learned in our syllabus. Do you all remember what concept this falls under? More ionic or less ionic? How come got range one? It all ties together to the concept of what kind of bonding? Can you all remember? Intermediate bonding, very good. Okay, so as we learned from that segment, right, we know that compounds are never truly ionic or truly covalent. It's always a mix of both. So in this case, I need you all to understand first, what are we comparing here? You all can refer back to your notes. What factor are we comparing when we look at Al2O3 and Al2S3? Are we looking at the cation or the anion? Anion. Okay, guys, when you look at the anion, what's the factor? Ionic radius. Good. Okay, so I want you all to recap this segment. Okay, we try to explain using this method. Not charge density. Charge density is cation. So guys, if the ionic radius, right, can I ask you, O2 minus versus S2 minus? The ionic radius is larger or smaller? Would be O2 minus versus S2 minus has to be smaller, right? Because O2 minus is higher up in the periodic table, so less quantum shells. Next, if you have smaller atomic ionic radius means what? You can follow the rules. What do we have? Okay, all the valence electrons and all that, yes, but the most important point is what? Having a smaller atomic radius means the electron cloud is, okay, electron cloud of O2 minus is actually less easily polarized by Al3 plus, the cation. Yeah, I suggest you guys go and write down this explanation somewhere in this question. Okay, because it's still related to what we've done before. Okay, smaller ionic radius, the electron cloud is less easily polarized. This is the point that you need to write in your explanation. Okay, so take note of it. Okay, so is electron cloud that gets polarized? Don't tell me O2 minus is less easily polarized. That's wrong. Okay, only the electron cloud must be mentioned. Okay, and guys, if you are less easily polarized, that means what? You have more electron sharing or less electron sharing? Less. So if you have a lower degree of electron sharing, it means you have what? Less sharing results in less covalent character, right? Because sharing is covalent. So lower degree of covalent character. Now guys, take note, you never know what they can test. If I were to test this question, I will ask you guys to justify your explanation. I will ask you to justify using the Van Hacker triangle. That's part one. And then part two, I'll ask you to justify based on the ionic radius. Then you have no choice. Okay, now you need to explain using two ways. So they can test like this, and then we need to be prepared for it. Guys, if you have less covalent character, it implies you are. This question is about ionic, right? So less covalent character implies you are more ionic. Make sense? So it all works out, it doesn't matter. Okay, you use Van Hacker triangle, you use intermediate bonding, both ways will work. See, one small question like this can talk about so many things. Okay, so this is how you study. Okay, relate it back to the concepts you learned before. Any questions? No? Okay, with no questions, okay, we're gonna proceed to the third question. This one's a bit more advanced. So let me show you guys what is necessary, what is required. I need you all to look at question 3, right, and just read part 1. We are gonna attempt part 1 first, part 2 we will do together. Okay. Yeah, I'll tell you guys what is necessary here. Okay, part 1 asks you guys to draw a hydrogen bonding diagram, which we have done before. Okay, so I need you all to try this yourself. If you do not know what ethanol is, okay, I'll tell you all first. Okay, ethanol is CH3, CH2OH. Okay, that's all I'm telling you guys. Okay, and if you're wondering, what are all these things? Do you all have any guesses? What are all these zigzag lines on the structure? Okay, carbon and hydrogen basically. Good. Okay, so I am going to tell you guys that this zigzag only contains carbon and hydrogen. That's it. Everything else is printed already. Okay. I think that's enough, right, for you guys to do this question. Right, give it a try. Okay, let's draw on the diagram here. Okay, so draw on the above diagram. Let me just take a look. So, okay, although pair drawn on the wrong side, it must be involved in the hydrogen bonding interaction. You join class section. Oh, you guys are long time classmates, is it? Or is it just sector? Well, quite long term. Yes. Okay, let's go through the answer here. Okay, so part one, right, is okay, you can already see what this question is about. There's application involved. Okay, something about COVID, washing hands, and all that. Yes. Okay, so everything here has to do with intermolecular forces. Number one, hydrogen bonding. Okay, so can you all recap, right? What's the criteria for hydrogen bonding? The first molecule must have what? Okay, FON. Okay, that's the second criteria. Second molecule must have FON with a lone pair of electrons. Okay, but the first criteria was what? Hydrogen bonding, right? So you must have a H bonded to F, O, or N. Make sense? Okay, either one of them. Okay? Okay, so each molecule must fulfill one of these criteria, right? Can I ask you all, this lipid molecule fulfills one or two? Okay, it only fulfills criteria 2, right? All the oxygens are bonded to just carbon. None of the oxygens are bonded to H directly. So we know that lipid must fulfill criteria 2, which means ethanol must fulfill criteria 1. Does it fulfill number 1? Does it have a H bonded to a O? Yes, it actually does, because O is bonded to a H. So this is the first criteria. Okay. Now, meaning to say, I need to see the OH on ethanol being used in some sort of hydrogen bonding interaction. Over here, this liquid has oxygen with lone pairs everywhere. Here. Every single oxygen here has a lone pair, so you can use any oxygens you want. I'm going to draw two possible answers. Okay, so if you want to use this oxygen here, go ahead. Okay, but you just need to interact with an H on the ethanol. So you do something like that, H2CH3. And then afterwards, fill in everything that you need to fill in as well. Okay, your partial charges, take note, guys. Partial charges must come in pairs. So I need to see a partial charge pair here and a partial charge pair here. Then they can form the hydrogen bonding interaction. Okay, I've already taught you guys what is the necessary criteria to be placed into your diagram. So I'm going to repeat that one more time. You need to have partial charges on each molecule. You need to have the lone pair of oxygen, and you need to have the hydrogen bond label. Finish 3 things. So that's if you want to use this particular oxygen. Okay, but some of you guys, they also opt for this oxygen here, and that's possible. Now you see this oxygen has a negative charge, right? But it doesn't matter. Oxygen has a negative charge, but you can still attract the H. Something like this. Okay, so it still has a lone pair. You bond it to the H. Now the H here, I need to see partial charges. But guys, can I ask you, is there a need to draw a partial negative charge on this oxygen? No need, right? Okay, because I'm sure you all can see, negative charge already attracts the partial positive charge. So here you don't have to put the partial negative. If you want to, it's okay, but it's not necessary. And then from there, you just label the last thing over here, hydrogen bonds. Now you just need to draw one. Okay, both answers are acceptable. Any questions? Yes. Okay, if you have to draw into this O also can. This one, every single O is possible. Okay, but I just want to caution you guys, if there's a negative charge, right, there's no need for you to place the partial charges. I mean, if you're scared, right, you put also correct. Okay, can? Any issues? Okay, okay, with that said, right, we're gonna do part 2 together. Okay, so I just need you guys to read through part 2. You don't have to write any answer yet, okay, because the phrasing for this question is a bit challenging. Okay, but what I need you guys to try, right, is just read through the question first, and later I'll ask you guys some questions that will build us towards the answer. Okay, so maybe in your head, right, you can try a bit first. Okay, use the logic in this context, right, to try to answer this question. Okay, after all, right, this is about soap and viruses and washing hands. So, and you know how washing hands are like, so you might be able to draw some parallels from your own experience into this question. Okay, so I'll let you think about it first. Okay, then later we will do it together. Right? Right. Okay, so I'll give you guys a bit of time to think about this answer first. Okay, then now we will do this together. Okay, I want to ask you all, right, how many players are there in this question first? Okay, you must identify all the stakeholders. So how many are there? Okay, we have 3, right? Okay, we have soap, we have lipid, sorry, and there's water. Okay, so you can treat it as if lipid is the virus. So imagine the virus is on your hand and you want to wash the virus off. So that's why you apply some soap, right? Okay, so you rub your hands with soap. Okay, so at this point, right, you should know soap and the virus should form some sort of interactions. Okay, do you think the interactions are strong or weak? Okay, I just very general term first, nothing to do with the technicalities first. Okay, strong or weak interactions. Okay, why weak? Okay, guys, imagine this. If you want to get rid of the virus, should the soap form strong or weak interactions with the virus? Should be strong, right? Okay, because if it's strong, then it will pull the virus particles away from the hand, right? Okay, if not, if it's weak, the soap is going to get detached from the virus particle and your virus will still be on your hand, which is terrible. So you need to have some sort of intuition regarding this context first. So in this case, let's just answer the question. When they say soap and lipid, it's basically the soap and the virus. What kind of interactions do you think they will form with one another? Okay, so that's where we will have to look at the actual molecule itself, right, and identify the type of interactions. Okay, so guys, lipid is right here. Okay, let me just erase all the junk. Okay, all these are the alcohol from the sanitizer. Okay, we are not using sanitizer in this case. Okay, we are using a soap particle. Okay, so soap is right there, lipid is right here, right? Okay, so we only learned a few interactions. Guys, let's consider any possible answers that you all have. Soap and lipid. Any possible answers? Okay, you say PD, why? Okay, good. Okay, you can see there are a bunch of polar CO bonds over here, right? Okay, so definitely PD is possible. Okay, but wait, when you say polar and you see oxygen, why can't they form hydrogen bonding? Why can't they say hydrogen bonding? Are they able to form hydrogen bonds with each other? Why cannot? Okay, good. Okay, either molecule there's no H bonded to an O, right? Here is still carbon bonded to O. All this is still carbon bonded to an O. Take note, all these zigzag lines represent carbon. The hydrogen is bonded to each carbon, but it's invisible. Okay, we will learn that in organic chemistry. Okay, but for now, okay, they can only form PDP attractions, yes. But guys, are there any other interactions that they can form as well? Okay, why ID? Can you all justify a bit? Okay, why is ID also a possible interaction? Okay, guys, because you all have to look at it from this perspective. PD is for the polar regions, right? And the polar regions are all these oxygen bonded regions. Is that the majority of the molecule? I hope you all realize, right, that the molecule also has a bunch of carbon and hydrogen atoms. Can you see that? All these big ass carbon chains are they polar or non-polar? Non-polar, correct? Based on what I told you all, C and H is non-polar. Now, there's a reason why they draw such a huge chain of carbon atoms. It's because it's to imply that the ID attractions are very significant. Because it's such a large electron cloud, and a large electron cloud implies rather strong ID attractions. So you cannot ignore the fact, right, that, oh, this is polar, yes, so it's PD only. No, the very non-polar, the large non-polar alkyl chains also have ID attractions. Okay, it's possible to have multiple attractions in molecules. Okay, so far? Can, Okay, then now, guys, we've answered the first point. You look at the second point. Okay, you wash your hands with the soap, right? But then eventually you need to use water to wash it away, right? So soap and water must form some sort of interaction as well, because the question says so. So guys, we have our third player, which is water. Can I ask you, our water and soap forms what kind of interactions? Okay, good. You have water here, and water is the molecule that you need, right, to have OH bonds. So in this case, soap and water must have hydrogen bonds, correct? And I need you all to understand, right? It makes a lot of sense. Now imagine, guys, soap and water, the interactions are very weak. What will happen in real life? If the interactions between soap and water were very weak, that means if you use water, can you wash away the soap? No, the soap will still be on your hand. That's a horrible piece of soap. Okay, you need to use good soap that has strong hydrogen bonds. Okay, once it attaches itself to water, that's how you can wash it off very nicely. Okay, can? And I want you guys to now look at the two interactions that we have just discussed. Guys, between these two parties, right, okay, what can we now discuss? Because the final portion of our answer is to address how it's able to break up the membrane. The keyword being breaking the membrane. Basically, the lipid molecule. Guys, I ask you all, what can we now discuss? What can we compare now? The strength. I mean, that's the only thing we can compare, right? Okay? You can see that water and soap forms stronger attractions than between soap and lipid, correct? So guys, when water comes in and washes away your soap, it will take away the soap, right? But at the same time, what will happen to these attractions? You'll break. Because these are stronger, it washes it off, these attractions will break. And as the attractions break, that's how the lipid, which is the membrane, also breaks apart. Does that kind of make sense first? Okay, so you can think of it this way, if you can't really make sense out of this. You know, you can see the documentaries where the eagle comes in to swoop the fish from the water very quickly, right? It's the same idea. You can think of water as the eagle, and then it comes in to swoop away the soap. But by stealing away the soap at such a high force, right? Because water, you know, there's a lot of force. Okay, it will also break apart these attractions. You force the lipid molecules to break apart as well. Okay, so that's how you answer this one. Okay, yes, pretty much. Okay, it's stronger than this, so that's why it allows this to break as water washes away the stuff, the soap. Okay, if you understand, water will wash it away, right? That's why it helps to break this apart as well. Okay, so some of you may be thinking, wait, isn't it still on your hand? Okay, but it's just broken apart. But I mean, isn't that what it's meant to do? It's meant to break apart the lipid membrane so that the virus is now inactive. Okay, so then after that, the rest of the water can wash away the broken fragments of the virus. Make sense? Okay, so that's kind of like the idea here. Okay, so application questions like these are not easy to phrase. Okay, so I'll show you guys how to answer this question. Okay, I split it into three parts. We're going to do the same thing. First, you can tell me, okay, soap and lipid, okay, can form PD-PD attractions, but you need to specify where. It is the part that a lot of students will specify. Okay, you can form PD-PD attractions between their polar regions. Okay, you can basically just mention this. Okay, and ID attractions, okay, between the non-polar alkyl groups. Okay, so I know this is only tested in like J2 when you learn organic chemistry. So maybe I tell you all first, all these zigzag lines, right? They are non-polar, yes, but we're gonna call them alkyl groups now. You don't have to understand this term right now, okay, just for the sake of this question. Okay, you just know what it's referring to, can already. Okay, so I very clearly specify PD is the polar regions, ID is the non-polar alkyl groups. So it's very clear like this. Then you answer the first part. Okay, then the second part is to mention what do you have between soap and water. Soap and water can form hydrogen bonds. Okay, then you immediately go straight into comparing the strength, okay, which are stronger, okay, than the PD-PD and ID attractions, okay, between soap and lipid. So the second point is to talk about soap and water's attractions and to compare its strength with whatever that is already between soap and lipid. So you can, honestly, drawing out this diagram is very useful. Okay, you can really play around with different ideas first before you go and write your own answer. Okay. So now, right, the third point, right, is really very contextual. So you try to phrase your own answer yourself. Okay, how this works out, okay, it doesn't have to be strictly the same as mine. Okay, as long as it makes some sense, open-ended, they'll give you the mark. Right? So you can say things are thus, water is able to wash away, okay, and break apart the membrane. Something like that. Even if you don't really know how to phrase your answer, right, at least maybe like paraphrase the context a little bit. So the word wash away, right, is a keyword in this question. Okay, you want to wash it away, you want to like break it apart, something like that. Okay, so that's also part of the answer. So again, I'll identify attractions. And then because of the differences in strength, you're able to wash away the soap while breaking apart the virus particles. Make sense? Yeah, okay, so that's kind of how what they are leading you guys towards. And also application practice not easy, right? So with that said, any questions? Yes. Okay, polar regions you can specify because of the polar oxygen regions, you can say that. Okay, but again, the lipid molecule has like phosphorus, oxygen, carbon, oxygen, so don't need to specify with you so much. As long as you make some sort of effort by telling me polar regions, right? It's honestly enough already. Yeah, okay, can. If you want to go ahead, your answer will be more nice, I guess. Okay, so now let's move on to the next question. Okay, I need you to try part 3. Part 3 is also not say very easy, okay, but I need you to try it yourself. Okay, they have some context in that as well. Okay, maybe I'll give you guys about like 2-3 minutes. Just think about an answer for that part first. Okay, then later we shall see. They ask you guys to describe the interactions, and they ask you to explain how it arises. How it arises means how it comes about. Okay, but for now, I just need you all to maybe think of what interaction is formed between fiber and dust. Don't need to explain anything yet. You just have an idea in mind that we'll discuss this together. Okay. Okay, so let's discuss this together. Okay, any possible answers here? What's the interaction between fiber and dust? Any guesses? Can I hear from you guys? Then we try to dispel any answers that you might have in mind. Okay. Okay, so you say ID, okay? So there's a common answer, right? Chloe, how about you? Any, okay, also ID, right? Okay, so ID is not actually the correct answer here. Okay, because, right, okay, go back to how ID comes about. ID is instantaneous induce. Okay, it's for what kind of molecules? Okay, mostly for non-polar molecules, right? Now, I'm sure you guys see dust and you think it's non-polar. Okay, dust between dust particles, right? Yes, it's ID because they're all non-polar particles, right? Okay, but now you're trying to form with fiber. You must first ask yourself, right, what on earth is fiber? Is fiber a polar molecule, a non-polar molecule, or what? What even is it? You take a look at this. Okay, they say that fiber is positively charged, right? Which makes it a what? Okay, it's not polar actually. Polar, right, is something that has partial charges. But they say that this guy has actual positive charges, which means it is fundamentally a what? Ion. Yes. Okay, fiber is an ion because you literally see charges there. Okay, don't be tricked into writing as a polar molecule. Okay, so we have an ion with a non-polar molecule. Is there an answer that's very close to this? Okay, so it can't be ID. ID is between non-polar molecules, but now we have an ion. So ID is out. Okay, but there's an answer there's one interaction that we have learned that's very close to this answer. Can you remember? How many interactions have we learned? It's actually 4. We never just learned 3 interactions. Okay, can we list down the 3 first? ID, PD, hydrogen bonds, it's all increasing in strength, right? And then the last lesson I actually mentioned there's a 4th interaction that's actually stronger than hydrogen bonds. Ion dipole interactions. Okay, come, we go and see this first. When we look at ion dipole interactions, it's between what and what? Okay, we specify first. Ion dipole is between an ion, obviously, and what kind of molecule? What kind of molecule has dipoles? Polar molecules. So take note, ion dipole is the 4th intermolecular force that we have learned before. Don't ignore it. Okay, so between an ion and a polar molecule has a dipole. But in this case, guys, can we just write ion dipole? No, right? Because dust particle is a non-polar molecule. They purposely say so. So, what's the possible answer here? Okay, so ion dipole is very close to the final answer. So, let's take a look. A dust particle is non-polar, right? Can I ask you, the electron cloud, is it symmetrical or not symmetrical? Okay, good. So I've actually taught you guys this when I first went through ID attractions. Guys, if the electron cloud is perfectly distributed, are there any partial charges? No. So if there are no partial charges, does it allow it to attract to the positive side of the fiber? No, there's no attractions, right? But cannot be, because guys, can I ask you all, if you put this evenly distributed electron cloud near a positively charged region, what do you think will happen? It will attract electrons which are negatively charged, right? So in this case, you can see that the electrons will flock towards the left side. And the right side will have less electrons. You can see that? So similar to what we've gone through in class 2 lessons ago. But can I ask you, now the left side of the molecule has a what charge? Negative charge. And then the right side has a partial positive charge. Good. Okay, again, don't write negative and positive because this is a simple molecule, not an ion, so it only has partial charges. Guys, can I ask you what kind of dipole is this? Is it a permanent dipole? Was it there permanently from the start? No, so this was induced. This was created by who? It was created as a result of the fiber particle. Can you see that? The word induce, as I've explained in class, means it's created by something else. It's influenced by something else. In this case, it's influenced by the fiber. You see, everything we learn in class has some sort of application. Just bring it back only. So in this case, guys, what do you think is the interaction between this fiber and dust? It should be ion dash what? Ion and induced dipole interactions. What we learned in the notes is ion dipole. It's between an ion and a polar molecule. When we say ion dipole, the dipole is implying a permanent dipole. But here we clarify that it's induced. We never learned this in our notes, that's why this is a tough question. But the principle behind it we learned before. So to answer the second part of this question, right, it's quite easy. How do these interactions arise? Mostly is the polarization of this electron cloud. So you can tell me this. The electron cloud, okay, of a dust particle. So you can now relate it to the context of this question. Okay, is polarized by the positively charged fiber particle. Can see that? All I'm doing over here is putting things into context. Don't just tell me the electron cloud of a non-polar molecule is polarized by cat ions. That one has no relation to the question. Okay, so contextualize it. Then you can tell me thus creating an induced dipole. Now then the rest is just ion. Ion don't need to explain anything. Okay, so that's the end of the answer. Okay, 1 mark each. You identify the interaction is 1 mark. Explanation, second mark. You may not have seen this phrase before, but you've definitely seen the way electron clouds are being polarized before. So it's all application. You can see, not easy really. Okay, Ken? Yes. Yes, you're supposed to come out with this yourself. Okay, but this comes with experience. This is a Hua Zhong prelim question. It's not meant to be easy in the first place. So don't worry. If you guys can't come out with this now, it's completely understandable. Okay, but I tell you in advance, okay, then now you're already better. There's some grade 2 students, we can't even come out with this because the chem bonding fundamentals are horrible. Yeah, okay, so good. Okay, come, let's finish up part C because part C is very easy. So sometimes you can see the 2 marks in part C is a lot easier to get than the 2 marks in part 3. Okay, so give it a try. Okay, this one I give you all like 2 minutes. I'm pretty sure you all can get the 2 marks. Okay. Okay. Right, okay, let's go through. Okay, so for structure and bonding, okay, what's the structure of copper? Giant metallic, lattice, good. What's the bonding? Okay, you can just go straight to metallic bonds between. Okay, must specify between the. Okay, good. So must say copper 2 plus cations. Okay, don't just say metal cations because it's in context of the question. Okay, so a simple question like this, they can penalize if you don't relate it back to the context. So between copper 2 plus and the C of, sorry, what was it again? Delocalize valence electrons. Yes. Okay, so you the common mistakes where people lose marks for this simple question is not relating back to the context and not specifying the word valence. Okay, so that's the answer. Okay, good. Okay, we're gonna try one more short part of the question, right? And then we take a break afterwards. Okay, so for now, what I want you all to turn to, let's turn to question 6. I think question 6 is a good question. Okay. All right, so for question 6, I need you all to try A part 1 and A part 2 only. Or perhaps, wait, okay, never mind. We try A part 1 first. Because this question takes a little bit of time because you need to draw the structure first. Okay, so A part 1 and A part 2. Okay, we do A part 1 first. Okay, so I'll give you guys 4 minutes. So 2 minutes per mark, so quite a lot of time. Right? I highly suggest you guys draw the dot and cross diagram for this structure first, okay, before you can determine all the shape and bond angles. So spend a bit more time on this. Okay, you also need to show the bonds between O and H. Okay, so they put that OH as a group, right? But O and H also have a bond. I suggest you all draw that also, because we still need to use that concept for later. Right? Okay, so I think roughly you all can get the arrangement of the structures correct. Okay, so it's quite clear that boron has to be in the center. And it's surrounded by which atoms? O or ZH? Should be O first. Okay, it's surrounded by O because no O is bonded to H. So we know that this should be our arrangement. Okay, by putting this as our arrangement, right, at least we know that there are actually 2 central atoms. Okay, I want you to take note. We haven't gone through an example with 2 central atoms before. Okay, but this is how it looks like. Okay, B is not the only central atom because oxygen is also a central atom because as long as you're surrounded by 2 side atoms, right, you're considered a center with respect to yourself. Okay, central doesn't mean legit the center of the molecule. Right? So with that said, oxygens will have shapes and bond angles applied to it as well. which we will discuss later. Okay, now we just draw out the structure. Okay. Okay, first you draw the structure first. Okay, then I'll tell you what to do also. Okay, you all can get the structure. Alright, okay, we go through the structure first. Okay, for compounds with more than one central atom, you must get the arrangement correct first. Generally, hydrogen must be at the outskirts of the compound. It doesn't make sense for hydrogen to be the center ever. So you put hydrogens on the outside, and guys, the general tip is this: you should work outside in. You should work from the outside with these hydrogens and then slowly feel your way towards the center. Okay, guys, because our hydrogen can form how many bonds? Just one bond. So you can get that done very quickly, just by doing a one bond each, something like this. Okay? And then right after doing this, you just fill up the rest of the bonds for oxygen and boron. Guys, I ask you, how many bonds are there between boron and oxygen? How many bonds? Okay, so you ask yourself first, oxygen is a central atom, right? Oxygen can form how many bonds generally? 2 bonds, right? Okay, so it has 1 bond on the left, so here must be another bond, single bond. So meaning to say, you just do something like that for each one of them. So oxygen double bond, so you do something like this. Oxygen, you just have to fill up everything else. So you should get something like that. Okay? And then you can work your way towards the center. Boron has how many valence electrons? Okay, 3, right? So all 3 valence electrons are drawn. Now after bonding, boron has how many valence in total? 6. Guys, are you able to have 6 valence electrons? Yes, right. It's possible to have less than 8. And that idea, right, we'll look at it later on. If you have 6 valence electrons, by the way, it means boron has what? Okay, say again. If boron has 6 valence electrons, that means it has a vacant orbital. Okay, very good. Okay, so boron has a vacant orbital. We shall see later on what this vacant orbital is used for. But for now, let's talk about the question. This question is trying to ask you guys to determine the shape and bond angle. Now, you guys can just refer to the notes and just write down the shape and bond angle, yes. But the catch over here, guys, is they want you to relate it back to the VSEPR theory. Okay, that part is the hard part. Okay, not the part about getting the shape. That one everyone can do. Guys, you all must understand what is the principle behind VSEPR theory. What is the essence? You don't go and copy the definition. That one doesn't get you anywhere. Okay, you must understand, guys, what is the principle behind VSEPR? Electron pairs like to arrange themselves as far apart as possible, right, guys? But what is the overarching idea? Why are they doing all this? Why are they going through so much trouble, right, to be as far apart from each other as possible? What is their one and only objective? Minimize repulsions. Guys, let's go a bit further. It's not in the notes. But if you minimize repulsions, it means you maximize what? Sorry? No. Okay, so you think about the idea. You want to make the compound as less repulsive as possible so that the compound is more stable. Okay, very good. Okay, so guys, the whole idea is to maximize stability. That's the overarching idea in chemistry. Okay, so over here, I want to take note. Okay, we can reference the answer, reference the theory. Do not copy down the theory. That one doesn't get you anywhere. Okay, so what I want to tell you is this. Okay, I'm pretty sure you can count that there are 3 bond pairs and 0 lone pairs around boron. Okay, boron is the central atom here. We're not talking about oxygen. So list down how many bond pairs and lone pairs are. Now I know there are no lone pairs, right? But I need to mention it as well. Okay, the lack of lone pairs also contributes to a unique shape. So 3 bond pairs and 0 lone pairs. Hence, okay, let's say, okay, in order to minimize repulsions. And you can even say to maximize stability, which is not necessary, but I think it's good. Huh? So to help you understand why we are studying VSEPR. Okay, VSEPR is a core idea, right? So that the compounds are as stable as possible. That's why you have so many wonky shapes and bond groups. Okay, so in order to minimize repulsions and maximize stability, the bond pairs arrange themselves as far apart as possible on boron. So you notice, I am not copying down the definition. I am subtly making references to the definition. And I'm only capturing the main essence of VSEPR instead of copying every single word from the definition. So you notice that's answering techniques. You immediately go straight into the objective, which is minimizing repulsions and maximizing stability. In order to achieve this, what do you do? Make sure it's as far apart as possible. And that's why you can link to the final part. Hence, you arrive at trigonal planar shape. Okay, so hence boron has a trigonal planar shape with a bond angle of what? Bond angle is 120. So again, I'm not interested in whether y'all can get the shape and bond angle correct, because y'all can just simply look at your notes. Of course, eventually y'all must remember this yourself. Okay, but here are the keywords. Always count the bond pairs and lone pairs. Okay, and then afterwards, okay, you make reference to the core idea. Hello. Okay. Sorry, which one? I haven't seen you for the chem morning lesson yet. No need. No need. Okay, we haven't go through finish yet, so you can't do. You want to come here and sit down also can. Yeah, then just sit down. No worries. Hey, you know we know lesson later, right? Huh? Yeah, I do it as a Sunday, that's why. What? Yeah, it's a Sunday. That's why I thought we just talking. Yeah. My, let's just come and chill first. Wait. Yeah, but I can just chill here first. Okay, can? Okay, so this is how you answer part 1. Okay, guys, I'll leave it to you guys to do part 2 together yourself. Yo. Start a bit late today, so about 6:45. You need a class? You do, right? I'll use outside later. Okay, can? Alright, guys, I need you all to take a look at part 2 now. Right? Okay, part 2, I think you all can do this yourself. Okay, because I kind of show you guys the structure of the OH3, so it can be easier. Okay, just fulfill whatever you need to in that question. Okay, then right after we're done with this, right, we take a short break. Okay?
No, like he told me like 3 lessons in a row that I had no lessons to do.
How many next year?
That's the one I'm it's not because I practice you practice just that. No, you know, like you follow people to the class, but it's not doing the type. 30, yeah, try 30, yeah. Cut I didn't do that again. So like, that's where I was then thought, oh, I would do that now. But I don't know if you do it. Amazing. So I won't do it. You asked me. Yeah, I asked me. I didn't understand. His study means like his was study. Yeah, what they were. Oh, it's just okay then, okay then. mechanical also. But what can learn with that? So I think if you actually identify actually yeah, it's not your class actually like every day here, it's just that now like your class really the so it's for beginner learning. So wait, isn't the graph oh, okay. In Twitter class is it? Why not as in page? Or like the Shana's last one class. Oh, you know, but then I thought already go to your class also. Oh, no, I'm just class. I mean, you're already very. You're already very teacher and you don't go to the other class. I don't know, that's how topic. Oh, yeah, yeah, yeah. No, something new. Okay, sorry. Yeah. Yeah, they're so bad. Not for the eating. Not it's for the. Yeah, my friend proposed to me. My friend concluded. No, she did not.
Gossiping, gossiping about. It's your structure. How come suddenly here the boron bond to the cage? Oh, shit. I'm distracted. I'm distracted.
So people just come when they make the stuff.
Just you. Just you.
You're so casual about it. I was like, no.
I mean, like, if you want to crash, it's fine. I mean, there's no one else here. No, I just figured that what I can forward today at class. Yeah, after this I have something on. That's why I can't have class.
Anyways,
Okay, come let me see. Okay, BCL3 is fine. This one is yeah, okay, good. Okay, they also want you guys to do one more thing, which is to label the dative bond. Okay, so since they want you to do it, just label. Okay, so BCL3 I think it's okay. Now, dot and cross, I think you guys are okay. But I want you guys to do one more thing. Okay, so before I take our break, right? Okay, I want you all to do one last thing for me, which is to convert it into the structure, including the shape. Okay, so I just draw first. Okay, your BCL3, right? You don't have to account for the shape first. Okay, you all just need to draw something like this. Okay. Okay, what I'm more concerned with, guys, I need you to convert this into your shape. Okay, so basically structure with the shape included. Okay, so convert the dot and cross into that. And then I also need you to do the same thing for BOH4 minus. Okay, you all notice you all can just fill off BOH3, right? The only additional thing is an OH minus ion. Alright. Now we also mentioned before, minus charge must add to the oxygen, right? So guys, one of the oxygens now has how many valence? 7, right? Okay, so what we've been doing just now, everything else here is the same. The only difference is the last guy. Okay, so I need you to take note. Over here, right, the reason why you can form BOH4 minus is because an OH minus ion donates a lone pair into boron via a dative bond. Okay, oxygen here has 7 valence electrons, so it only forms a single bond with H, something like this. Okay, but because you can form a single bond only, right? Okay, you can't form a second bond, so you can only use a dative bond here, something like that. So that's for 7 valence, and you have the minus charge. Now, what I want you guys to do now is to convert this guy also into the shape. Okay, but the shape, just be very careful. We have multiple central atoms, so I need to see both shapes being reflected. Okay, so for now, okay, just go ahead and find. Okay, because usually dot and cross is not the final thing. They want you to draw the structure. It's good practice, okay. The more you practice yourself, okay, then the less you will have to refer to the notes in future. Okay. Okay, come, let's take a look. Right, so I'm pretty sure BCL3 is quite simple. Can someone tell me what the shape of this guy is? Trigonoplanar, yes. You can always recite it to yourself in your head. It is all for the purpose of memorizing this. Okay, so go and write it down as well. This guy is trigonoplanar, and I also want you all to write down the bond angle. Okay, 120 degrees, quite simple. Now, the special thing over here, right, it's for POH4 minus. Currently, we have two central atoms. Guys, let's look at boron first. Can I ask you all? Boron has what shape? Okay, what's the shape around boron? No, it's actually not. Okay, guys, I think I know why y'all got trigonopyramidal. It is tetrahedral because this guy over here is now a dative bond. A dative bond is a bond pair. Now he is not a lone pair, so that's why you count wrongly. That's why you got trigonopyramidal. Okay, a lone pair has been converted into a dative bond, so you should count it as a bond pair instead. So now it is 4 bond pairs and 0 lone pairs. I should see a tetrahedral shape, something like that. Can you see this? Okay, so I draw the oxygens first because these oxygens are the side atoms compared to boron. So now let me just write this out first. For boron, right, is tetrahedral. What's the bond angle? 109, good. Okay, this is a common bond angle, must memorize. Next, we have another central atom, which is oxygen, right? Can I ask you what's the shape around oxygen? Okay, not linear. Okay, linear is wrong because we have 2 bond pairs and 2 lone pairs, which gives rise to a band shape. So the band shape is also reflected over here. I need to see the band shape like this. So on all oxygens, right, it needs to look bent. So I guess this one can bend this way. Okay, very important. No, it's everything surrounding oxygen. So what's surrounding oxygen? It's not only H, but also B. Can see that? Okay. Why are you a center? You are a center because you're surrounded by at least 2 side atoms. Okay. If you only take into account O and H, right? Is there a central atom if it's just O and H? No, there's no center in this case. So when there's a central atom, there must be minimally 3 atoms involved. 2 sides and 1 center. So this is all about perspective. Boron is in the center between 2 oxygens, or 4 oxygens actually. The oxygen here is in the center of 1 H and 1 P. So you must take into account everything. Does that make sense? Okay, so here is a band shape. Now to put this complete structure, right, I need you to put the lone pairs of oxygens. Because you have to understand when you all draw these kind of structures, right? The lone pairs must only be shown on the central atoms. You don't show me the lone pairs on any side atoms. Okay, in this case, the side atoms have no lone pairs anyway, so it doesn't really matter. Okay, but as you can see, there are 2 shapes. Oxygen is bent at 105 degrees. So these are some of the more complicated structures, right? When you have more than 1 central atom, you'll see more of this eventually. Okay. As for now, also don't forget there's a dative bond giving from the oxygen to boron. You just donate straight to boron. Why can you donate to boron? Because earlier on we did mention this, right? Boron has a vacant orbital. So that's why it can accept the extra electrons from oxygen. That's why it's from O to B. All good with this? So the dot and cross, yes, I know it is enough for the question, but I don't think it's enough for revision. Revision, you must do this yourself, even if it is not prompted. Okay, Ken? Now, okay, let's just finish up. Okay, since we only have one more thing left to do for today. Okay, this is a rather long question. Can you look at part 3? Part 3, right? I know they only give you guys 4 lines. Okay, high chance you will need to exceed the lines. Okay, because there's quite a bit to write. Okay, so for part 3, I want you guys to give it a try. Okay, then once we're done with this, we're going to be done for today. Then I'll give you guys homework from this worksheet. Okay, so go and try part 3 first. Okay, try to the best of your ability. Then we'll go through this together. Okay, I don't think 2 marks will do it justice. Okay, I'll give you guys about 4 to 4.5 minutes for this. Okay. Okay, about 30 seconds left. Just finish up your answer. If let's say your answer later wrong, you want to rewrite your answer, you can just write it at the back when you can find any space. Okay. So let's take a look at our answer. Okay, so melting point question. Okay, so roughly about 5 minutes, I would say is a good amount of time for this question. Okay, so I would say that this is very demanding for just 2 marks. Okay, for 2 marks, you need to write this much and fulfill a lot of criteria. Okay, but let's recap a few things first, a few principles. Okay, so you look at the 3 compounds, they first ask you guys for structure and bonding, which is the first core idea in this chapter. Okay, then afterwards, to explain differences in melting points, is either discussing differences in bond strength or you discuss intermolecular forces. So we have to identify the class of compounds first. Okay, guys, what's BCl3? What kind of compound is it? Okay, simple covalent. Okay, don't just say covalent. How about BOH3? BOH3 is also simple molecular, right? Okay, how about NaBOH4? Giant ionic. Yes, okay, good. So we have simple molecules here, and then we have an ionic compound over here. So we can already see how we can split our answers. Simple molecular giant ionic, right? We can already tell that giant ionic has the highest melting point because melting points of, the strength of an ionic bond is the strongest. So you can talk about NaBOH4 by itself, which I'll talk about in the second paragraph. But for the first paragraph, it is a comparison question. We are supposed to discuss why this guy has a higher melting point than this guy. Now recap a little bit first. Okay, guys, they are both simple molecular structures. Okay, they both have simple molecular structures. Okay, but what are we supposed to compare here? Now remember, guys, for simple molecules, when we compare melting and boiling points, what's the first thing that we need to compare? Can you remember? If you are given 2 molecules, you must compare what and what? Sorry? Okay, intermolecular forces, yes. Okay, but what's the factor that we're supposed to zoom into? Always compare the electron cloud size. Yes, okay. So I mentioned before, no matter polar or non-polar, right? You should always compare electron cloud size first, because this explains the strength in ID-ID attractions. And guys, all molecules, all simple molecules have ID-ID. So this is a valid factor for us to consider first. But if this doesn't work out, guys, then what's the next factor that we dive into? Okay, not about charge, nothing about charge, simple molecules have no charges. But if we cannot compare size, then we talk about the types of intermolecular forces. Perhaps hydrogen bonds are stronger than PDB, right? Okay, and let's just say in the very small off chance that the type of intermolecular force is the same, then we will go to our last factor, which is to look at the factors within each type. This is the rare case in which the type of intermolecular force across two molecules are the same. So following this idea here, can I ask you all, BCl3 or BOH3, which one is bigger? Which one is larger in size? B actually is Cl3. A lot of people think BOH3 is larger, but you're going to count up. B and 3 is the same, right? So we just need to compare Cl and OH. Cl MR is 35.5, OH MR is 70. So it's quite clear that BCl3 is larger, right? Now run through this very quickly, guys. If you have a larger electron cloud, what does that mean? Larger electron cloud means more easily polarized, leading to stronger ID-ID attractions. Remember all that from the notes, but does that fit this question's data? This guy may have stronger ID-ID attractions, but clearly it is not enough to explain why the melting point of this guy is higher. Make sense? So we cannot use electron cloud size in this question. So let's move to our second factor. Can we talk about the type of intermolecular force? Okay, let's identify, guys. BCl3, what's the intermolecular force? Okay, BCl3, you have drawn the structure just now. Is BCl3 polar or non-polar? Non-polar, so it's held together by ID-ID attractions. What about BOH3? BOH3 is held together by hydrogen bonds. Good. Okay, you have O and H, right? Definitely hydrogen bonds is a polar molecule. And hence, guys, we can now compare the strength. It's quite clear that hydrogen bonds are stronger and require more energy to overcome, which fits the data in this question. Does that make sense? Okay, so you have to take a look. Okay, sometimes this question is all about picking the correct factors. Okay, I know this guy has stronger ID, but clearly it is the hydrogen bonds that are more significant to the point where it can contribute to the higher melting point. So you talk about the second factor instead. Can see that first? So here there's no need for us to relegate to the third factor. All good? Okay now? And then the next one should be quite simple now. Okay, you have identified this correctly. As a giant ionic lattice, okay, it has strong ionic bonds, or you can just say ionic bonds, between the cation ion and the anion, which you need to specify. Between Na plus and BOH4 minus. Don't tell me cations and anions, that one's not specific enough. Okay, it's very clear that ionic bonds are stronger than intermolecular forces, right? So that's why it has the strongest bonds, most energy to overcome. Okay, what you can also do is this, the ionic bonds in the sodium borohydride, whatever this is, are stronger than the hydrogen bonds in BOH3. Okay, so you can compare the next strongest thing. You don't have to compare to the weakest. Compare with the next strongest thing, which is hydrogen bonds. That's why it requires the most energy to overcome. Why I use the word the most energy is because this guy is the third one, right? Okay, two compounds, you change your language up a little bit. So guys, this is the ideal way you can explain this question. And that's why I say 2 marks is a bit demanding. Okay, I would say this is more suitable for a 3-mark question. Okay, maybe by the time J2, right? Okay, you have J2 is a very long time from now. So this one should be very comfortable for you guys by then. That's why I say 2 marks by then should be okay. Okay, 3 marks for now. All good with this question. Let me quickly write down the homework that I want you guys to do. Okay, it's basically the most of the rest of this worksheet. Right? Okay, so for homework, right, I need you all to finish question 6. Because question 6 is good, we haven't finished yet. Okay, I want you all to do question 8. Okay, and then do question 4, 5. Basically, the entire worksheet except for question 7. 7 is not that important, so I don't really care now. Okay, it's just a dot across compound which we have done before, so honestly doesn't matter. Okay. So finish up the tutorial first. I know Chloe is submitted already. I will send it back to you in a while. Okay, it's okay. It's okay. Again, I don't push you guys for it unless it's taking like 3 weeks or 1 month. Yeah. Okay. So yeah. Okay, take your time to finish up your answers, quality answers. Do that first. Tutorial first. Okay, then after mark and give it back to you guys, then you can send me the answers for this one. Okay, so that kind of concludes chem bonding for quite a while before like May or June when we revise chem bonding. Okay, then next lesson we're going to start on gaseous state. Okay, and yeah.